Welcome to the rigid body equations of motion. Today we're going to discuss tensors. The object that we have discussed previously, namely the operator I, is a tensor of the second rank. In three-dimensional Cartesian space, a tensor T of nth rank has 3 to the power n components, which we can label as T with n indices, that change under an orthogonal transformation of coordinates A as given by the law here. So you see it involves many applications of the orthogonal matrix in question. In 3 dimensions, a pseudotensor transforms as a tensor except under inversion. So we have the same rule of transformation, but in the case of an inversion, we once again have involved the determinant of the matrix A, and with respect to a parity transformation, we have the rule here. A tensor of rank 0 is a scalar, while a tensor of first rank transforms as seen here. So one application of the orthogonal transformation, and by virtue of formula 4.12 prime derived in chapter 4, it follows that a tensor of first rank transforms like a vector. In the case of the second rank, the law is given here. So a second rank tensor T and the square matrix formed from its components are different objects. It is important to state this fact. And this is due because a tensor is defined only in terms of its transformation properties under orthogonal coordinate transformations, while a matrix is unrestricted in this regard and can be considered independently from a particular class of transformations. In practice, however, in the specific case of orthogonal transformations, the two are equivalent, namely, and this is because by virtue of the similarity transformation of a matrix T, we find out that its components transform exactly like in the case of a tensor. In the case of two vectors A and B, we can define an object called a dyad by the rule here. And if we write its components out explicitly, we can put them together in this form. And notice that when transforming a dyad, so this implies that we need to transform each of the vectors. So we see that the dyad transforms just as a tensor of the second rank. And as a note, we can define a unit tensor in terms of the Kronecker delta, as here, and tensors of lower rank can be obtained through successive contractions. So from a tensor of second rank T, we can obtain a tensor of rank 1 or a vector by such a contraction through a dot product to the dot product to the right of the tensor, but we can just as well have a dot product to the left of the tensor, and if we take dot products both to the left and right, we can contract the tensor into a scalar. In the case of a dyad, furthermore, we have these particular relations that hold true, and they are both seen quite trivially based on the definition of the dyad. So, in summary, we have defined tensors of rank n in three-dimensional Cartesian space in terms of their properties under orthogonal transformations. Based on their transformation properties, we have identified scalars and vectors as tensors of rank 0 and 1 respectively. We have shown that tensors and their matrix representations are equivalent under orthogonal transformations, and we learned how to obtain tensors of lower rank through the contraction of a higher rank. In the following, we will put this to use in discussing the inertia tensor and the moment of inertia. So with that being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.